are occurring above the slab. So the plate is coming in, it subducts, it melts, the magma comes up, and the volcano is directly above the subduction zone. Okay? So all of these processes are related to one another, so they all occur in the same geographic regions. Any questions so far? Yeah. So again, the little red dots, what? Yeah. That aren't, exactly. So most of the red dots are related to subduction zones, okay? So, all of these along the Aleutian Trench here, the Kuril Trench, all of these are related to the Java Trench here. These are all directly related to subduction zones. But there are also some exceptions, as you pointed out. Hawaii is a key exception. Obviously, we're going to talk about that. Any other questions? Yeah. So any volcanoes that happen within the plate. So again, Hawaii would be an example. So this is the entire Pacific plate, right, with a ridge to the south and east, and then the subduction zone to the north and west. And so Hawaii is pretty much right in the middle of the plate. So Hawaii is a special case. So let's in fact go on to this. So this is the different settings where you can have volcanoes. And so we just talked about volcanoes in subduction zones. So here's an oceanic lithosphere subducting down beneath a continent. And as this goes down, it's heated up by the surrounding mantle. It starts to melt, and that lava works its way up to the surface and erupts in these big stratovolcanoes that you have in subduction zones. Okay, so that's setting number one. Setting number two, and here's another example. This is an ocean subduction zone, but it's the same process. You have subduction of oceanic plate. It melts, the lava rises up, and you have these volcanoes. So Japan, the entirety of Japan is these ocean volcanoes. Okay, the second region is the mid-ocean ridges. So here's a mid-ocean ridge in the middle of this ocean, and all along these sections here are volcanoes. And so you have these long, continuous ridges of volcanoes that are erupting constantly to create the new plate. And then the third type of volcano, which is unusual, or is less common at least, and is the case for Hawaii, is what's called hotspot volcanism. So this is an example of a hotspot. So you have a line of volcanoes here. So just focus on this first hotspot labeled D here. So the idea here is that you have a hotspot, which is a column, or rather the hotspot is immediately beneath the lithosphere. It's a relatively warm mantle, and so it melts, and that melt then comes up to the surface. All right? So these are believed to be due to mantle plumes, these plumes of hot material that are gradually upwelling through the Earth's mantle. They reach the surface, they start to melt, just like they do at mid-ocean ridges, and that's why you get volcanoes. And then this line of volcanoes here, because this plate is moving, so this plate is moving towards the subduction zone, the hotspot stays stationary, and so as this plate moves, you get a series of volcanoes because this plate is being pulled across the top of the hotspot. Okay? So those are the three primary settings for volcanoes: mid-ocean ridges, subduction zones, and then these hotspot volcanoes. And Hawaii is a great case example of these hotspot volcanoes. So when it comes to the plumbing, as we zoom into one of these volcanoes, the plumbing doesn't matter what type of volcano it is, it's all pretty similar. Starting at the top, of course, you have a cone. That's what we always see, is the cone at the surface. And the shape of this cone depends on the type of magma which is moving into the volcano. There's a magma chamber, typically fairly close to the surface, people in the crust. People typically think that the magma chambers are between about 5 and 10 kilometers depth. This particular cartoon doesn't really represent that very well, but the magma chambers are typically at about 5 to 10 kilometers depth in the Earth's crust. And then, of course, that magma chamber has to be being fed from melt that's deeper. So in continental environments, for example, or in the oceans for that matter, there's going to be this lithosphere, the Earth's lithosphere. We've not really talked about that, but this is the relatively rigid outer layer of the Earth. It's shown here as being 75 kilometers thick. So all of the melting, all of the flow in the mantle goes on at greater depth, and then as this material upwells for whatever reason, it melts, and then the melt is less buoyant, and it works its way up through cracks in the lithosphere and forms the volcanoes at the surface. Okay, so that's sort of the anatomy of a volcano. Any questions? Yeah. Yeah, that's what I don't like about this. The way that this cartoon is being drawn is that the black is the crust, and in the case of the oceans, the crust is about 7 kilometers thick, and then this sort of brown, grey region is the lithosphere, the subcrustal lithosphere, and in this case it's shown as being 75 kilometers thick. So this shows this volcano here being significantly thicker than the crust, which is just not the case. So the Hawaii volcano, for example, from the seafloor up to the top of the Hawaii volcanoes is about 8 kilometers. So the total height of the volcano, it's a massive volcano. So it's about 8 kilometers. The thickness of the oceanic crust is typically 7 kilometers. So it's about the same thickness. So this picture's kind of out of scale. Any other questions? Yeah. Sorry, speak up, I can't hear. Is there a certain rate at which the magma flows up to the surface? You mean at this stage or at this stage? Down here? So people debate how quickly this material flows up. I don't think we know is the straight answer. I'm going to show you some seismicity actually in Hawaii, which we think is tracking the magma moving through the lithosphere and the crust. So actually, let's look at that and see what that rate turns out to be. Other questions? Okay, so I want to tell you about there are sort of two primary end-member types of volcano: shield volcanoes and stratovolcanoes. Okay, so we're going to start by talking about shield volcanoes. So shield volcanoes, they're called shields because they look like a shield, i.e. they're very broad and they're very flat. Okay, so this is a shield volcano, much broader than it is high. And the type of environment where you see these are seafloor spreading and hotspots. You see these in environments where you just have oceanic material. There's no involvement of continental material. Okay, and when you only have oceanic material, then the silica content of the lava is lower. So if there's less silica content in the lava, then the lava is relatively low viscosity, meaning it's more runny. It can travel greater distances more rapidly. And as a result of that, you get these broad and low types of volcanoes. So these are the types of volcanoes you find at mid-ocean ridges, and these are the types of volcanoes you find at hotspots like Hawaii. So Hawaii is a string of shield volcanoes, and they're fairly well-organized volcanoes that you have magma chamber at some depth, typically some sort of vent, maybe a collapsed caldera, and then lava flows out of these vents at various times. And so the analogy here with Hawaii is that the Hawaii Volcano Observatory is actually at the main caldera, which would be this central caldera. But the eruption, the magma is coming out of a separate little sort of source of the eruption that Michael was talking about at I forget what it's called, Pu'u'o'o or something? Somebody help me out? Pu'u'o'o, thank you, Sierra. Okay, so that has been where the magma has been coming out of that little eruption crater for many, many years, for decades at this point. Okay, and so in this analogy, this would be the main caldera, which is active. It does have magma, but it's not erupting and hasn't for a long time. But then there's this little side chute, which is where the lava is coming out today. Okay, so question, yeah. So the question is, what's the mineral composition of the flows? So actually, let me answer that when I'm going to show you a flow, and we'll talk about it at that point. Okay. Okay, so this is shield volcanoes, low silica content. Actually, I'll talk about it now. So low silica content. The mineral content, this is basalt. What comes out of this? The rock type is called basalt. And the mineral composition of this basalt, it contains orthopyroxene. Oh dear, we're testing my geologic knowledge here. Orthopyroxene, it contains some quartz, but not very much quartz, and feldspar. I'm looking at the other people in the room who might want to correct me. Nobody wants to correct me. Excellent. Okay, then now that's definitive. It contains three primary minerals: feldspar, orthopyroxene, and quartz. And the difference between these kinds of eruptions, which is basalt, so the relative concentrations of those three minerals, it has low silica content, so it has more orthopyroxene, less quartz, and less feldspar. And then that's what we call basalt, and it looks black in color. All right. The black in color is because there's more, the ratio of felsic minerals is higher in shielded volcanoes than the other type of volcano. Okay? So, case example of this is Hawaii, as we were just talking about. So here's Hawaii. Michael was just talking about, this is the site, this is the main caldera up here, and then this is the site where the magma was coming out, and so this is the stuff that was flowing directly towards the ocean that somebody was asking about, and the lava flow that Michael was just talking about is actually propagating off in this direction. Okay? So the town that Michael was talking about is right about here. But what you can see, from this is a topography map, so you can see that this currently active part of the island is a pretty small-scale volcano. Mauna Loa, with its peak right here, is a much larger volcano, as is Mauna Kea, which is over here. And then there's another sort of volcano up here and a smaller, older volcano over here. And so this is a hotspot, which means that the plate is moving over the top of the hotspot. And the Pacific plate, is actually moving in this direction. So it's moving up to the northwest. And so this is the new volcano. These are slightly older volcanoes. And then the other Hawaii Islands, of course, are all up over here. And that's because they've been dragged away from the hotspot over a period of millions of years. Okay? So here is the view of Mauna Kea from Mauna Loa. So we're standing on Mauna Loa right here, and we're looking across this big valley, here towards Mauna Kea. To give you a sense of the scale of these volcanoes is just huge. And then this shows a recent eruption on, I think, in Kilauea. I'm not 100% sure. And you can see these are these rivers of lava. This is a little different to what Michael was showing. This is a much larger volume eruption where there's a lot of lava at the surface. It's coming out at relatively high elevation, and so you're seeing these rivers of lava flowing down. And you can see that where it's grey is where it's formed a little bit of a crust on the surface, and where it's orange is where that crust is broken. So this is different to what Michael was showing. This is much faster moving lava, and so that's why it's not able to form a good crust, which is what the flow that Michael was talking about shows. Okay, any questions? All right, so how do we monitor these volcanoes? How do we deal with these potential eruptions? I mean, Michael was talking about how you deal with the lava flow right now, but before that eruption started, or before an eruption starts, how do you know that the eruption is coming, and how do you sort of get ready for that eruption? Well, the way that you do this is by monitoring the same kinds of instruments that we use to monitor earthquake activity. You can use to monitor the little small-scale earthquakes that are generated by the movement of magma. So I'm going to show you some data from Mauna Loa. So this is the network, so GPS sensors that are tracking the very small displacements of the surface of the volcano, seismometers to record earthquakes deep beneath the surface, tilt meters. So as the magma comes into the volcano, it causes the sides of the volcano to tilt out, right? So you're inflating the volcano, you're pushing the volcano up, and so the sides of the volcano tilt out. Strain meters are just to see the degree to which the surface is deforming. There's just two of those, or three, I guess. Those are the main instruments. So sort of GPS, seismometers, and tilt meters are the primary instruments that you use to monitor if a volcano is active. If there's no signals, there's no movement, there's no earthquakes, then you can feel pretty confident that we're not about to have an eruption. And in the run-up to an eruption, you start to see these kinds of signals, and you can start to say something about what might be about to happen. So I'm going to show you a sequence of seismicity from Mauna Loa. It's from a while ago now, but it kind of illustrates the process and the difficulties associated with trying to predict when the volcano might erupt. So we're going to start back in 1971. And so this just shows a number of earthquakes at all depths, between 0 and 5 kilometers, 5 to 15 kilometers, and greater than 15 kilometers depth. Okay? And so here's a map. This is a zoom in to the peak of Mauna Loa. And so this is the actual caldera. So this is kind of where you might expect the magma to come out. And these earthquakes are colored by depth. All right? So what you're actually seeing here is that in April of 1974, there was an increase of seismicity. And it was relatively sort of mid-depths, 5 to 8 kilometers depth. Remember what I just told you, that these volcanoes are about 8 kilometers above the sea floor. All right, so they're about 4 kilometers. The water depth is about 4 kilometers, if I remember correctly. So they're about 4 kilometers above sea level, and they're about 8 kilometers beneath the sea floor. So when you see seismicity at 5 to 8 kilometers depth, that means it's actually within the volcano. It's not in the ocean floor beneath the volcano. It's kind of at the base of the volcano. All right? And then, as time went forward, by the end of 1974, moving into 1975, the seismicity gradually got shallower and shallower, and you can see it sort of migrated to the southeast here. But of course, remember that this distance, here we go, 2 kilometers. So it's migrated about 4 kilometers, but it's come up about 4 kilometers as well. So this is really seismicity migrating pretty much straight up beneath the volcano. All right? So by December 1974, the seismicity had gotten much closer to the surface, and by February 1975, this is just prior to the eruption, you could see the seismicity very shallow depths and very close to the caldera. So no surprises as to what happened next. In the middle of 1975, there was an eruption out of this caldera, a relatively small eruption. And so this is what you can see here, right? So we had this gradual increase in seismicity. It started out at depth, it got shallower, and then we had the eruption, and it shut off. Okay, so once the eruption finished, the seismicity shut off. And there was very little. Then in 1984, basically a decade later, the pattern started again. We started out with some deep seismicity, and then some shallow seismicity. So again, it's migrating up towards the surface. But no eruption. Nothing happened. And then complete quiescence after this. Okay, so nothing going on for a very long period of time. And then in 2004, some very deep seismicity started, 70 kilometers depth. Okay, or sorry, I guess 40 to 70 kilometers depth. Okay, so very deep seismicity. So this is now down in that lithospheric layer that we were talking about at the beginning. So this is at the base of the lithosphere, the rigid part of the Earth's outer shell. And there was this very deep seismicity directly beneath the caldera, as you can see. But remember, this is at 40 to 70 kilometers depth. And then it just stopped, and we haven't seen anything since. So nothing since 2004 beneath Mauna Loa. And so the question becomes, is there a cycle here? And can we use this cycle to predict when we might expect to see an eruption? And clearly there is a cycle in the sense that there's deep seismicity and then it becomes shallower and then there's an eruption. That clearly is a cycle. Just the same way as we have an earthquake cycle, we know the plates are moving, you see the increasing deformation, and then one day it pops. The challenge with volcanoes, just as the challenge with earthquakes, is to know exactly when it's going to finally happen, when the eruption is going to start. And that is still just as challenging, or still challenging, just like we can't do it with earthquakes. We can do better with volcanoes because you can see when the lava starts to get very close to the surface and you can issue some warning that you're expecting a volcano to erupt. But it may happen in a matter of minutes, hours, days, but potentially even years. And so you can issue some kind of warning, but the time frame for that warning is very challenging. That's what Michael was talking about. People know that there's going to be more magma coming out of Kilauea. There's people who live, they know that they are in a path that a lava flow is going to take from that volcano at some point in time, and the question is whether that's going to be today or whether that's going to be several decades from now. And so how you deal with that is obviously something of a challenge. When it comes to earthquakes, you deal with it by making your house stronger so that it should be able to withstand the shaking. If that lava flow flows through that town, there is nothing that they're going to be able to do to save their homes, obviously. Okay? At least they know they can get out. because it's a slow-traveling lava flow. Okay, so the other type of volcano is what's called a composite volcano. You know, actually, what I'm going to do is I'm going to stop here, and we will continue with this lecture on Thursday. And yeah, we'll continue this lecture on Thursday, and I'm then going to actually ask you to watch a NOVA video on volcanoes after Thursday. Okay? Before everybody gets up, who has Michael's rock? Excellent. Can you bring it to me? Thank you. Okay, thank you. See you all on Thursday. Okay, and please be sure to write your GSI name and your name on your certificates, okay?